Greetings! In this video, your group consisting of Jesulín Domínguez, Ignacio Aguilera, Nicolás Jiménez, and Mikaela Maldonado will be presenting two tools of quality often applied in the realm of civil engineering. The first tool is the Pareto chart, which used for quality control, more specifically, prioritize the most critical problems and focus the control where it is most appropriate. The second one is the Ichikawa diagram, used to identify the root cause of a problem and support the continuous improvements of the process. We'll be explaining how each of these tools work and then present a real case where they were applied in construction process.
First, the Pareto chart, a tool based on the 80-20 rule, which establishes that an approximated 80% of the effects come from the 20% of the causes. This method is used to identify which are the factors that most influence a problem, allowing the priority efforts where they will generate the most impact. To prepare it, data of the problem, such as the type or frequency of failures, is complete order from most at least important and represented in a bar chart. Then a cumulative curve is added, showing what percentage of the total effect each because represents. With this, we can determine which few cases concentrate most of the what constitutes this problem, guiding the decision making towards action that offer the biggest benefit. In this example, a research paper used Pareto chart to identify which seismic related deficits account for most of the problems observed in a Chilean bridges using data from more than 500 bridges between 1920 and 2010. Each structural component and seismic prediction element was classified according to our national design criteria. After ordering these by frequency and impact, the Pareto analysis showed that three deficiencies alone: lack of seismic stoppers, undersized bearing lengths, and the use of expansion joints constitute 8% of all seismic performance problems. Additional recurrent issues such as poor bearing, support, construction, and differential perceived lengths also contribute to this dominant group. The resulting Pareto chart here allowed the authors to prioritize which elements require detailed examination and regular lifting, confirming the patterns observers observed in other independent data.
Now, with the tool for continuous improvement, the Ishikawa diagram, or the cause and effect diagram, is a tool used for the analysis of a problem, identify all its possible causes. It summarized form of presentation, as in this example figure, looks like a fish skeleton. The body represents the branch of the causes, and the head would be the main problem. These causes are grouped in categories, which in civil engineering are usually the following six: manpower, materials, machinery, methods, mother nature, and measurement. The main advantage of using the diagram is force the team to think in a structured way by not focusing on just the most evident issues, but on the most harmful. It is a tool of continuous improvement because it helps to find the origin in an issue and propose definitive, permanent measures.
As for the example, we have this study about the pathologies found in steel structures of a variety of buildings in various locations in Brazil, where the Ishikawa method was applied to determine the main causes of these reported structural failures, based on previous investigations during and after the building's construction. From these recurrent pathologies detected by users, the study breaks down each problem into the standardized categories known as the 6M, which, which were the ones mentioned before. The objective here was to determine which categories truly intervene in each pathology and which ones didn't provide relevant info. For each one of those, like infiltration, cracks, corrosion, leaking or detachment of slabs, etc., a detailed list is made as a quite more extensive version of the diagram, enumerating all possible causes for each of the M's and indicating which ones are associated with the failure in question. For example, in infiltration, the analysis concludes that the causes were mostly manpower and methods, due to the inexperienced labor and mistakes with the material specification, with the machinery section here not even applying in this case. Another issue, cracks in the closures, the causes come exclusively from the method used, with a great variety of possible causes listed, but only three being the ones affecting it. The issue below, sound transmission through walls, had no causes in any of the 6M's influencing the issue, meaning that the problem has nothing to do with the steel structure. And so on until we finish with all the pathologies. We can then add up all the causes into which of the 6M's they belong, thus giving us the fact that half of all the issues encountered in this analysis were caused merely by the method used. Finally, the study uses this distribution to feed a GUT matrix where all the previously discussed causes are weighted according to gravity, urgency, and tendency, so we can properly rank the criticality of the problems. That concludes our Track 6 video. Thanks for watching.